Something that I didn't cover last time, we'll start out with it here, is called the Universal 7-Part Data Circuit, which is nothing really overwhelming, I guess is a word. We have DTEs, and in the data world, we have DTEs and DCEs, data terminal equipment, data communications equipment. And a DTE connects to a DCE if you're going interface to interface. That's a big deal in routers because if you connect a serial interface to a serial interface, one of them has to be a DTE, one of them has to be a DCE. DCE's got a clock rate. That's the only real difference in a router. So it's a data communications equipment. When you're connecting to an ISP, the ISP typically provides the clock rate, so you normally aren't going to have to worry about it. But in this thing, the DTEs are things like computers, it says laser printer, computers, printers, fax machines, a credit card reader, a router, some device that has an interface. In this one, the DTE to DCE interface on the computer is the computer bus where we plug the NIC into the computer bus. So we have a DTE, and we have a DCE and a DTE interface. We have one of those on each side, so that takes care of 6 of the 7 parts of the data circuit. And then we have the transmission cable and channel cable between them. DCEs connect to DCEs using channel cable. Now, when we connect a computer to a switch or a hub, that's not a DTE, DCE arrangement because the DTE, DCE happens inside the computer. When we connect the wire in, we're in the channel communications equipment, the channel cable. If you use an Ethernet port, a fast Ethernet port on a router, that's not a serial connection. These are for serial connections, and typically you're going to see them on a router, but in the computer we don't really see it. We have the DTE, which is the machine itself, and this kind of puts us in this OSI frame of mind, doesn't it? Because where does the computer fit in the OSI model? Outside of it. It communicates through the OSI model. The OSI model is, again, a communications model. Does it really work that way? Now, most people don't use all 7 layers. The TCP/IP model uses 4 layers. NetWare had 1. NetWare had their own communications model before there was an OSI model. It had 3 layers. So why do we have it? It allows for compatibility. It allows for standards. When we go from IPv4 to IPv6, well, I got to change the IP portion of the communication stack. We don't have to change the data link layer. We don't have to change Ethernet. We just have to change the IP component. And what allows that is the modularity of the model itself. So the 7-part data circuit, nothing complex, but how do we get from point A to point B? And we get back over here at the other end, we got DTEs, we got the computers, the same things again. We're going from, then this one we're going from a computer to a server. The topic tonight is fiber, and I want to put this picture up because one of the things that happens in fiber, and then we'll look at some pictures and talk about it and look at fiber again, is what happens to light? What happens to a flash? You shine a flashlight into the woods, what happens to it? It gets absorbed, but it gets spread out, it gets dispersed, doesn't it? Mm-hmm. We have a similar thing happens in fiber, and this is just shows 3 parts of a piece of light going through fiber channel. As it bounces off of the walls, it gets refracted, not reflected, but refracted as it goes into this thing. So it changes the speed a little bit. It actually goes into the wall and gets refracted and comes back out. Not all frequencies do that. Some of them, this one shows one going right down the center, no refraction at all. Well, golly, that's going to get there before everything else. Depending on how far you go, and I guess the moral of the story is you have to be careful of which fiber you do, depending on the distance. If you're going short distances, it's not an issue. Multimode fiber, that one, it has multiple paths in it. usually used in a LAN environment. It doesn't go all that far. The long-range fiber is a single-mode fiber, a single frequency, single channel, and those are usually created with lasers. Let's see. Yeah, this one kind of gives a relative picture of what goes on. This says it's 100 micrometers, and this one's 50 micrometers. The fiber cross sections, you can find that probably single mode fiber is going to be about 8 nanometers. Multimode fiber is 62.5 nanometers down to maybe 50 nanometers. How big is that? Well, it's 8 nanometers. It's 8 millionths of a meter. It's not very big, as you said. Not very big at all. So we're putting this in a very confined channel. I got another one here, the Fiber Optic Association, and the cladding. This one shows, this is really weird. If you take the fiber optic class and they ask you how it gets there, it's actually refracted, but they call it total internal reflection. Total internal reflection is refraction. What is refraction? Now that I've used the term, what's refraction? Bounces off. Bounce bending. When light waves enter water, for instance, you ever done that? Try to touch something in water or put a rod in water and it looks like it's bent? That's caused by the refraction. As the light goes in there, it actually gets bent. So we have those sorts of things. Same thing happens here. The light goes in here, it gets bent. It goes in, it actually goes into it and gets bent back out. So this one has multiple paths. It's still got the one down the center. Some of the light's going to get there before the other light, and all of it's got signal on it. So you have to be careful of what you're using, which kind of fiber. This one shows a couple of different modes. You don't have to know these. These are just kind of for background. Multi-mode step index and multi-mode graded index. This one takes precautions to try to get everything at the end at the same time. Different speeds go out here and around, and you've seen that when if you watch racing or if you watch, all these war movies, what do they want to do if they don't want to use their brakes and they want to slow down? What do you do? You zigzag.
Really?
Well, yeah, because you can maintain your speed without actually and decrease your speed over ground. That's what's happening here. The faster ones are taking the longer path. The slower ones are taking the shorter path. So they get to these points at the same time. So you get to the end of the fiber at the same time. Single mode fiber, in the comparison here, single mode fiber is much, much thinner than multi-mode fiber, and it uses a single frequency light to do it. The single mode fiber is the one that's used for long distances. Multi-mode fiber, shorter distances. Not really necessarily the manufacturing cost of the fiber, but the ends that go on the fiber, the multi-mode is much more precise, hence much more expensive than the single mode fiber. Multi-mode, long distances, think lasers. The Fiber Optics Association, if you're interested in looking at fiber, they've got some kind of neat information there. So what we want to do tonight is finish up this thing, and as you can see by my bag of stuff up here, we'll make some wire, punch down, and I think what we'll do when we punch down over in room 110, they've got a wall that's actually, it's got a punch down block in it, things like that. We'll go over there and punch down as long as I can find the 110 blade. This one's got the wrong blade in it. When we talk about these things, and I know I digress from fiber, but when we talk about these things, and one of the test bank question sets that I see are 66 block. This is a 66 block. There's also a 110 block. There's a couple of videos on the Moodle page. One of them talks about a 66 block, how to punch down a 66 block, how to connect a 66 block, because you have to actually connect these things. And the other one's a 110 block and a punch down block. You can look at those things. Watch those videos as we do those. But we'll do those tonight. We'll make some wire, make a straight through and a crossover, and then we'll go over in there and do some punch downs and try out your straight through and crossovers with the cable testers to be sure that we actually made things that work and we got the whole system that works. So fiber itself, a lot of different types of fiber. We looked at the single and the multimode. All this stuff that actually not all this stuff, most of this stuff that I've been passing around to you is multimode. This is all multimode. I see there is in here somewhere, and I think it's this one, a piece of single mode fiber. You can see, does that say SMF on it somewhere?
Yes.
So this would be single mode. I had to look and see. It's all marked. Single mode. The rest of all this stuff is multi-mode.
As a single is better?
Single depends on what you're doing. Single will go further. It's also going to, yeah. Faster is kind of a relative term because it depends on, what's the speed of light?
We have
Really,
no
really,
idea.
really fast.
Huh?
I have no idea.
What's the speed of light? It's pretty fast, right?
Mr. Farm, thank you.
Speed of light as we go through these things. And back to the connectors, the ST, straight tip, SC, square connector, those kinds of things. And I think that they'll probably ask something like, which one do you do with a twist or without a twist? With a twist, the ST, without a twist, the SC. But when you look at them, you don't really tell the difference. We're not going to strip them off, especially that single mode. I borrowed that one months ago and never gave it back to the guy that gave it to me. So it's in here. That you can't really tell the difference, can you? Can you, Robert? I mean, they both feel about the same. One of them 8 nanometers. The other one, this gray stuff, is 62.5 nanometers. Is the diameter of the fiber, the piece of glass that's inside it. I think there's some of it here. Well, this is. We talk about the cladding. What this one is, and of course one end is gone. That's okay. But this is one that's spliced. And the way you put fiber together is splice it. You glue it. When you put the fiber onto the connector, splice it. Basically, you glue it to put it in here. But you get an idea of what's in here. And actually, this does have, now that I hold it far enough away, you can see here, this one, and pass it around. This is glass. Don't do it, cut you. I've cut myself with this stuff before, but you can kind of get an idea of how big the glass that's inside of all this stuff is. And what we're going to do is put light in it, send it from point A to point B. So fiber, this one, and we looked at this at the end of last class, has got all the outer jacket, the armor, and all that other stuff. Inside it are multiple fibers. And if you're going for a very long distance, actually the long distance fibers have thousands, hundreds of thousands probably of fibers in those long distance cables that they run. Because when we go to, if we were to run fiber to a computer, you have to have 2 fibers, one in and one out. When we do twisted pair, we have 8 wires. For up to the Cat 5 standard, actually most of the standards that we use 4 of those wires. 2 of them for transmits and 2 of them for receive. In the fiber, you got to have 1 fiber for a transmit, 1 fiber for a receive. So fiber, and this one has, if you can see, it's got multiple fibers inside a single casing, so that we could take it. I mean, if we went from here to the knock and we wanted to take a lot of different connections over there, we would not want to take individual strands. We'd want something that had multiple pieces of glass inside of it.
So is it considered simplex or half duplex?
It would be a half duplex. Simplex is a broadcast. Simplex, because simplex broadcast goes to multiple locations typically. These are point-to-point connections, so it would be a half duplex. When you put them together with the LC connector, we'll get all those terms back in here. With the LC connector that has the two fibers would be a full duplex arrangement, but you still have to have the two pieces of fiber in there. So one to transmit, one to receive. Single mode fiber, again, just more pictures of these things. What it's got, we got a jacket, a buffer, cladding that goes around this thing and a core. This one here goes down to 8 nanometers. When we go up, this thing goes up with a jacket and everything's 400 nanometers. So if that's 400 nanometers and we go to 8 nanometers, you can get an idea of how small the core actually is, the center of this thing actually is that the light goes through. Advantage to fiber is how far you can go before you have to repeat the signal. And they talk about different distances, and they're all different distances. You can have a very high signal loss because there's no noise. You don't have to worry about noise on the fiber like you do about noise on the copper, because if we get noise, we go across one of these lights or whatever, we're going to be able, we're probably not going to be able to do anything, but we could go a lot shorter distance, because as we get the attenuation, I'm trying to get these terms back in here, as we get the attenuation, the decrease in signal strength, and we have noise, once the signal level goes below the noise, you've got no hope of getting your signal back. You have to repeat it before it gets beyond that point. Don't have that issue. Don't have that issue with fiber. Fiber up to about a 98% signal loss. Coax, high resistance to noise, says expensive, and it is relatively expensive, also not used very much. Coax can go up to 100 megabits per second. Coax, when we go into the 10 base stuff, and I guess we should put some of those distances up here, huh? 10 base, 100 base, 1,000 base, so we'll put a 100 base T, goes 100 meters. A 10 base 2, what does the base mean when we talk about 10 base 2?
That's single channel.
Single channel baseband, different from broadband. So baseband, broadband, single channel, single frequency on this thing. 10 base 2, when you see a 10 base 2 or a 10 base 5, think coax. In 10 base 2, think 185 meters. 10 base 5, think 500 meters. I have no idea why 2 means 185 meters, but that's how far you can go with it. Fiber, all of them's a little bit different distance. They'll go anywhere from about 30 meters to 6 kilometers. There is different fibers used in for different applications, obviously. You may have a stereo. Some people have stereos that have fiber on them. You may have a speedometer on your car that uses the fiber. They use fiber in airplanes. You really wouldn't want fiber in an airplane that shatters when you land, would you? I wouldn't. Because the next time you leave, it's going to be in trouble. They use fiber on ships. You have to have things that are impact resistant. Those are typically plastic. The stuff that's here that's going around is in fact glass. It's spun glass. It's flexible glass, but it is glass. If you're working with fiber, be sure you take all the safety precautions, the goggles and all that stuff, and clean it up, because if it gets in your eye, it's in your eye. It's a piece of glass in your eye, and it does hurt. You can get it embedded in your hand, so clean up any of the residue that you have. I know that's a different class. But high resistance to noise. This has a high resistance to noise because it has a shielding around it. And you can go from, I don't have a piece that I can cut, you can go from anywhere from the woven copper that you see that when the cable guy comes in and puts in the cable TV and they strip it off, you can see the shielding around that. That's what gives you the resistance to the noise. Relatively expensive, relatively difficult to install. because it's not as flexible as the twisted pair. Not as easy to do. Impedance, the resistance that contributes to controlling signals expressed in ohms. We talked about that. Two different types of it. The thick wire, which you probably will never ever see. Thick net is a really old system. It used a thing called a vampire tap. If you ever hear the term vampire tap, it actually penetrated into the center core. It's kind of, well, kind of like if you put in and I don't know if people use it, put in an ice maker and you don't want to rewire the thing, what do? You got to get one of those little screw ends and penetrate the same principle. Same principle, but we got to get the thing to the core so that it gets the connector there. Thin net, 10^2 is this stuff, which is coax. It connects to everything with a T. Could go from one to the other. If we had multiples of these, instead of having these resistors on the end, we would just take this off, put our next station in and our next station in, and the end, and each end you have to have a terminator. If you don't have a terminator, it just doesn't work. Problem with this, and this is a real bus, this is a true bus, right? Everything's connected to everything else. This is where this was the original, well, actually 10^5 was the original, but this was the semi-original bus. And we used to have this, and students loved to play with you. If this becomes disconnected any place in the bus, the whole bus goes down. So it has to be connected from end to end. What they would love to do was to do something like this, make it look like it's connected. Like in Christmas tree lights, and then it wouldn't work. So now you got to go troubleshoot. I digress again. How do you troubleshoot something like this? Can't. Network's down.
Change your whole network.
Change your whole network. I bet I can troubleshoot it quicker than you can change the whole network.
Oh, yeah. Look how often you're going to have to troubleshoot. Walk through and find out.
Well, if you got students wandering around here about every third day. You divide and conquer. Anybody use electric fence, the invisible fence?
Yes.
What happens? What do you do when it goes down? Or it's not gone down on you? Mine used to break all the time.
You take a resistor, go to each station, and
No, it's just one big continuous wire. I had a roll of wire. I go to the middle. Go to the middle, then you measure the resistance back. If I get a zero resistance because it's just a piece of wire, 5 ohms or something like that, then that half's good. The half that has an infinite resistance, that's bad. Put it back together and go to the half, go to the middle again. You do the same thing with these. You go to the middle, put a terminator on each end and see which end works. That end's good. Put it back together, go to the middle again, do the same thing until you work it down. It's a lot quicker than going station to station if you got more than probably 10 or 15 stations on it. Those things are kind of a pain. But 10^2, 10^5, 500 meters. 10 is, what's the 10 and the 100?
10 and 100, 100 base 10, T is
100
100.
megabits per second, right?
Yes.
And the T, anytime you got a T, and honestly, I think there's one of them that's 30 meters, but if anytime that you got a T, you can just about bet on 100 meters as the maximum length for it. So there's really, when we get into that, they have this big table in the book about fiber, and then fiber can just drive you absolutely crazy. For certification tests, when we have fiber, I just always pick whatever the longest distance that they give me for the fiber. Coax, this is a picture, not a real good picture of a coax, RG58, 50 ohm, and it's all marked. And all this cable is going to be marked. That can be kind of a big deal. You have the right cable. Do you have Cat 5, Cat 5e, Cat 3, Cat 6, Cat whatever? It's all marked. So this one is that. This shows the outer conductor is a braided wire. It's got an insulator in here, polyethylene plastic, and an inner conductor. The reason it is called coaxial is it has a single axis and everything goes around that single axis. Twisted pair, color-coded pairs, insulated copper wires twisted together. The reason they're twisted is so that you have resistance to EMI, resistance to noise. The twists help cancel the noise because we looked at it the other day. If we have two parallel wires and we put the same signal on them, then they're going to amplify each other. If we can make those signals to be out of phase, another good term, right? Out of phase with each other. And if we have this one at a +5 and this one at a -5, then we wind up with somewhere around 0. It's not going to happen that way, but that reduces the noise. It doesn't stop the noise. It gives you some resistance, not some immunity, but some resistance to noise levels. The twist ratios, the twist per meter, twist per foot. The more twists, the more expensive, the better the noise rejection, and the higher the category number. So the twists per foot, Cat 3 is going to be fairly loose, and I don't think we have any of that in this stuff. Cat 5, Cat 5e gets more, Cat 6 even more twist, or 5e more twist per foot. The standards are TIA, EIA 568A and 568B, and there are pictures of those on the Moodle page. The levels, level 1 or Cat 3, 4, 5, 6, and on up to 7. These basically represent noise rejection ability as well as what the data rate is. Cat 3, the highest data rate of a Cat 3 cable is 10 megabits per second. Still 100 meters for the distance. What we have generally, as we change the frequency, actually we change the timing of the, to get more data on it, you change the timing or the amount of the distance between the packets. So if we had, let's say that we had these frames that were going at this rate, and you know I'll mess this up, and this is 100 megabits per, or 10 megabits per second because we want to go to 100. 10 megabits per second. The only thing that we actually do to make it 100 megabits per second is just put the frames closer together. Looks kind of dangerous. You wouldn't want to do that in your car, would you? No. Get a ticket for following too close. But that's effectively what you're doing, is that you're just making those things go across without as much separation as we had before. And twisted pair is the most common cabling. I'm sure everybody would love to have fiber, but it's really not all that practical. Just the cost to put in, we've talked about that, a fiber microscope around $10,000, and you can check the prices on that. I looked one up one time and said, gee whiz. The ends to go on the fiber itself's not really extremely more expensive than the copper, but the stuff to make it and the connectors really are substantially more. Most of it be a real big term, not most of it. They still make it here in Roanoke, yeah. Fiber Optic down the interstate here, yeah. And they're actually a well-known company, but there are lots of people that make fiber. You know how they make it? I'll see if I can find my video, huh? Well, I see, I did the break remind me to see. I had a video one time, and I don't know where it is, but I'll see if I can find my video that how they do it. They basically melt this glass, take it up real high, and drop it and extrude the glass. Yep. Shielded twisted pair, we talked about it, and I don't have any shielded. Unshielded twisted pair. Shielded twisted pair has shields around it, a full shielding or some sort of a shield, and it's for better noise rejection. So it's going to be a higher have a higher ability to resist noise. When you do that, what this really is a ground. You have to account for the ground when you put it into a connector. Unshielded Twisted-Pair is what actually I think most people use, what we use. Less expensive, less resistant to noise than shielded Twisted-Pair. It's easier to work with, easier to make, and it's not really not extremely difficult to make, and that's what we're going to make later tonight is Unshielded Twisted-Pair. And Robert's an authority on it. He's going to help everybody because he made 6,000. Probably felt like it, right?
Probably.
6,000 pieces of cable in the Middle East.
Like about 5 100-meter rolls. So.
Yeah, that's a lot of cable. Less expensive. The reason to make it is, one, to get the standards down and kind of understand what goes on. The other one is you may have to make one occasionally. Are you going to make this on a daily basis? We certainly hope not. In my opinion, if you can buy the commercial stuff, it's going to last a lot longer than the stuff that we make because it's made by machine. They can mold it better. Machine gets it more precise than you and I can. But occasionally you need a specific length. And in that case, you're probably just going to make it yourself, or you need something right now. You don't have time to buy it. The standards here, Cat 3, 10, 4, 6, 10, Cat 5, up to, and those Cat 5 goes up to 1,000 megabits per second. You can go up to gigabit speed on Cat 5 cable. You have to be careful, trust me, of your links, and you have to be careful of making it properly, getting it seated correctly. We've had a couple of them that they made around here and go from a gigabit port on the switch to a gigabit port on the switch in the knock, and it just said no. You plug it into the 100 meg port in the knock, and it said, okay, I can do 100, but I can't do 1,000. Yeah, I got to be careful about it. Back to the fluorescent lights that Philip was talking about. Those are real issues. Those are real issues. They put an awful lot of noise on them. So Cat 5e, higher twist ratio, better noise rejection. Cat 6, 6 times the throughput of Cat 5. And what was throughput? That's what you actually got through, right? The bandwidth was the bandwidth we call the theoretical capacity. It's kind of like cable modem. What's the theoretical capacity? 4 meg, right, or 5 meg, or 12 meg, or whatever you make. What's your throughput? Mine's probably about a meg.
At least about half.
Yeah. So the throughput's what you actually get. Bandwidth is the theoretical on these things. 6E and 7. Cat 7 signal rates up to gigahertz. Why do we care about the gigahertz, the signal rate? What was baud rate? The number of times, the number of changes, right? The frequency. So the baud rate of telephone is? Telephone is? We're going to do Chris because he keeps telling me the number. Oh, 2400 baud, right? Because it's audio. It's an audio phone line. It's not digital. The 2.4 gigahertz you're thinking about is wireless. Yeah. Well, I know. Yeah, except for all these guys using DSL, but they're using a different frequency, I think. So the frequency, the more changes you have, the more data we can have. Low frequency, fewer changes. The higher frequency, the more the changes. When wireless came around, there were 2 standards, the A and the B standard. The A standard was 5 gigahertz. The B standard was 2.4 gigahertz. The speed available on the A standard was 54 megabits per second. The stated speed for the B standard was 11.2, I think it was 2 and 11. 11 megabits per second was a tie-in. So the more changes we have, the more data we can put on these things. The quicker we can change the information. Unshielded Twisted-Pair, and you'll get tired of it before the night's over. It's just the wires themselves as we go through here. Copper wires twisted, and the twists and the twisted pairs are twisted within the wire itself. When you start making these things, you have to untwist them and kind of try to straighten them out, which is sometimes not as easy. Throughput, shielded and unshielded can go to 10. I mean, they both basically do the same thing, depending on the grade of the cabling and the transmission method used. Transmission method we use is what we're not to yet, whether we're using Ethernet, token ring, fast Ethernet, gigabit Ethernet, what kind of capacity we have at the ends to put on the media itself. Remember, the media is not part of the model. The media just connects the two things together. The layer 1 is going to have a lot to do with what goes on here on the device itself. Shielded, usually more expensive than unshielded, and that kind of makes sense. If you're going to put a shield in this thing, it's going to cost you a little bit more to make. It's going to cost a little bit more to buy it. Is shielded worth the cost? I don't know. We've never put any shielded in because we've never had any real issue, because we're not pushing the 100-meter limit in anything around here. It just doesn't go that far. Both use RJ45 and RJ11 connections. RJ45, 8 wires, 4 pair. RJ11, 4 pair is the way that it's made. It has the capacity for 6 wires. But nobody does that. Noise immunity, shielded obviously going to be more immune to the noise. Size and scalability, 100 meters. Here's the kind of the maximum number of nodes. And what's a node? Anything can have an IP address. 1,024. That's a pretty big network, 1,024. I think that if you're on a bus, you would not get anywhere. Just from the you wouldn't on a Windows bus, I can tell you that, because of the broadcast. Maybe once a day you'd be able to see a text document. But just broadcast, that's the maximum. That's one of those maximum theoreticals. The practical limit's probably going to be somewhere around 200, 250 machines. Shielded, twisted pair, and unshielded is just one that has each. Just shows the shield here around the wire itself. 10 base T, fault tolerance, capacity for component systems to continue functioning despite damage or partial malfunction. 10 base T, 10 is 10 megabits per second baseband T, twisted pair. 543 rule. We talked about that kind of sort of a little bit, right? The 543 rule says that in Ethernet, this is Ethernet. And after I go through it, I'll tell you why I said this is Ethernet. Ethernet has a number of requirements. 2 basic requirements is that it is a bus topology, and it uses a media access control, which we're going to do next time when we get to layer 2, called CSMACD, Carrier Sense Multiple Access Collision Detection. That's a mouthful, isn't it? That means that it waits to listen until the bus is clear, and then it sends, and it hopes nothing collides. If it does collide, then it goes back and resends. So the 543 rule, and back to the timing of these things, I know I'm jumping around, of these frames that go down the network, what has to happen is you have to be able to get from one end to the other and detect the collision. That's what dictates your maximum length. The 543 rule says that we can have 5 segments separated by 4 repeaters, and 3 of those segments may be populated. Okay, the key here is bus. When we get into switches, which we will do, never mind. When we get into switches, remind me to tell you that I lied to you. I didn't lie to you, but we use switches now. And the 543 rule really doesn't apply because there's no collisions. The 500 or the 5 segments, 500 meters for the T's, 2.5 kilometers for 10 base 5 is based on the ability, the timing, the speed of the data to get from one end to the other and detect a collision so that you don't create a collision environment. A bus, a true bus like this, has one collision domain is what it's called. One lane bridge. And that's what you can think of it as. Maybe a really long one-lane bridge, because only one station can be transmitting at a time in one direction. Unlike we're talking about full duplex, half duplex, and broadcast here, this is a true half duplex condition because one station can be transmitting, everybody else has to wait. That's going to slow things down a lot. That's why switches is probably the best thing you can do to your network. A couple of pictures here. This one is a little deceiving in that it doesn't have 5 of them. 5's the maximum number. This one's got 1, 2, 3, 4 segments separated by 3 repeaters, and it has 2 of them populated. This one shows 1, 2, 3, 4, 5 segments separated by 1, 2, 3, 4 repeaters, and we have 3 of them populated. And that's all based on the ability to do that. Fast Ethernet, 100 base T, is different than Ethernet. Fast Ethernet you're usually going to use in a switch, although this one shows hubs, using a switch, and when you use a switch, each port on the switch creates its own collision domain. I'm already into layer 2, I realize that. So you don't have the collision issues that you have with the bus. This one's showing a Fast Ethernet maximum distance between workstation A and B is, 300 meters, because we have a repeater. If we followed the same 543 rule, and we would have to with hubs because that would be a true bus. The 543 rule, we could go up to 500 meters. We could have 100 meters on this segment, 100 meters between them, and 100 meters on the second segment, giving a total distance of 300 meters between these things. When you start talking about the 100 meters and you start running the wire, that's not necessarily 100 meters horizontal, because you've got to come into the room, you've got to get from here, in this case from the switch to the machine, you've got to consider how far you're running in the room, what's the drop from the ceiling if you're going through the ceiling, or how far you're coming up under the deck plate if you're going from the floor. That's 100 meters total, station to station. Not, well, in this case we could do a hub to hub because we have repeaters in there. Fiber contains glass, plastic, reflects the light back to the core. We've already talked about that. This is a better picture of what a piece of fiber with multiple fibers in it looks like. Single mode fiber, we talked about it, I think, when we started the class. Narrow wire accommodates high bandwidth, long distances, and it's going to be expensive. Not necessarily because the fiber costs more to make, but because the connectors have to be so much more precise. Multimode, benefits over copper, nearly unlimited throughput, high resistance to noise, excellent security, on and on and on. Verizon has this service, and I don't think it's available here yet, called FiOS, which actually brings fiber to your house. I mean, they bring the fiber drop right to your house. Cable uses fiber, but the last mile's copper. I don't know what it costs, but I understand the FiOS, if you can get it, is pretty expensive. They started in Northern Virginia, and then they went to Tidewater, and I guess Richmond they're eventually supposed to get here. Multimode speeds greater than 10 gigabits per second. And we're getting to where we can get these kinds of speeds on copper. So is fiber going to replace everything? I don't really know the answer, but I would think that if you could do the same speed with copper, that's probably where you're going to stay, because it really does cost less. Costs less to put in, costs less to manage. It's the most expensive medium. 10 different types of connectors, and that keeps going up. Typically uses the ST or the SC connectors, and those are the ones that the guy read about, said you need to know for the Network Plus. Noise immunity, unaffected by EMI. Why is that? There's no copper in it. EMI, electromagnetic interference, needs copper in order to induce a signal. Needs a conductor. This doesn't have one. EMI, no EMI, great to use in a high EMI environment. And power station, radio. What about a radio station? Broadcast. I mean, at the tower, I guess, because you're going to have a lot of EMI there. And so fiber is probably going to be the media of choice in those environments.
Why doesn't it break?
Why doesn't it break? It does. You can break it, but it's just very flexible. I'll see if I can find a flashlight, because we can do it, and you can see that you can bend it. You can actually, if you bend it enough, it may, because you feel it is flexible. It's very flexible. If I tied it in a knot, I probably could stop it and maybe even break it.
I guess I was kind of picturing a bunch of little pieces in there together, but then you look at that and it's got the,
Yeah.
pieces
That one's
together.
installed, they avoid 90 degrees.
Yeah, oh yeah, you avoid, and you should do that with all of it, avoid 90 degrees. The reason they make the Cat 6 so rigid is so that you can't bend it 90 degrees. Anytime you do that, even copper, if you do a 90 degree bend, it's going to affect the flow. I was the main propulsion assistant on a steamship many years ago. It was 1,300 pounds, 275 pounds per square inch, 975 degrees Fahrenheit steam. The radiusing, the radius bends were very precise so that you didn't affect the flow, you didn't get condensation in the bend, so that you didn't get it going wrong direction too fast where you would eat into the piping with the steam, because that's pretty powerful stuff when you got something that high pressure. Was very carefully radiused, and you really need to pay when you're putting, as you can see around here, we don't pay a whole lot of attention to that, but actually they kind of did. This one back here, you got the nice loops and the patch cords, no real bends in them, and that's where you should be. That's not necessarily the best thing to do with all those loops, because remember, we could get some crosstalk in there. You get crosstalk to yourself, which messes things up. But this stuff is as you can see, is very flexible, and you don't want to do that. Will it break? Yeah. Is it hard to break? Yeah, but it is a very flexible glass. It's not like the glass that you drop in your house that shatters. Although, trust me, you can shatter it. The first one that I made, it said do this and polish it. Said, oh, I know how to do this. Shattered. Take the fiber microscope and you can look in there, and it didn't. It did shatter just like a glass in your house. So it will, but it usually doesn't break from bending because of the way the manufacturing process and the material that it's made out of. It's kind of like fiberglass, pretty flexible, huh? The fiber and the insulation, that's glass. When you get it all over, you know it's glass, right? So it depends on the, that's a good question. It just depends on, it's the manufacturing process that does that. This is the physical, this is the table that we're going to click through here real quick. But the T's, 10 is 10 in each of these is in the front end. The T's are all going to be 100 meters. 100 base TX, 100 meters, 1,000 base T, 100 meters. Here's one that's 1,000 base CX. This one's a little bit different. Twin axial cable is what it's called. It's 25 meters. FX, when we get into the F's and the L's and so on, we're talking fiber. They're going to be different distances. The T's are going to be twisted pair. That's what the T stands for. 1,000 base SX, depending on the motor or the SRs, those kinds of things. The cable plant, we're going someplace else. The cable plant, the whole package, the package itself. One of the things that you do need to be careful of, aware of in the cable plant is how you make the cable, where you run the cable, how you expose the cable. Not the topic really of, actually they do have some security questions, but not really a topic of this class. But in a security sense, you don't want this stuff laying out there so that just anybody can come up and connect to it, or anybody can come up and receive the signal. So you need to be aware of the environment that it's going in. We don't worry a whole lot about it in here because who's in here? Students. These rooms are normally occupied. But if you had a receptionist at your front desk and you had some live ports to your network in your reception room, or if you had an isolated reception room with live ports, you probably don't want that to happen because somebody comes in and plugs in there on your network. So be aware of those things when you put the cables in. There are standards for the cables, the 568 standard for commercial building and wiring. If you follow the standards, you're probably not going to get into any real trouble. The entrance to the facility point, where the internal cabling begins, the demarcation point, the demarc. That's where the ISP's responsibility ends and yours begins. It doesn't have to be outside the building. It can be inside the building. Huh? And they really hold you to it, yes, sir. They're not going to fix any of your internal wiring.
Years ago, they would come in and deliver
right to
your device.
Yeah.
And they would maintain it. But
but not now.
They won't even extend demarcs anymore.
And they are extendable, but you're right. They won't do that. Backbone wiring, connection between telecommunication closets. The backbone wiring here in this building, the quote backbone wiring unquote, would be these gigabit wires that go from here back to the NOC if we had a true backbone. And there's gigabit into each of the rooms, and if you'll notice on this switch over here, it doesn't work. It's in a 100 meg port because this is one of those you plug it into a gigabit port and it says no, thank you very much. We've checked it's gigabit on the other end, so what's the issue? I don't know, somebody needs to get up in the overhead and see which light it's going next to. And that would be my guess, is that it's probably too close to a fluorescent light, and that's getting so much noise on it that you can't interpret the signal at the other end. And we can do that if you want. We'll plug it in if you want. If you don't watch it not work, Sam's working on stuff. He probably wouldn't like that very much. But backbone wiring is dedicated wiring, typically high speed. Backbone is normally a higher speed. The backbone of the internet, there are a number of, and I used to have a single one, but I went and looked. There, if you go search Google for internet backbone, you'll get the speed and wiring of a lot of different ISPs, because there are a number of providers now that are part of it. It's mostly phone companies that are part of the internet backbone. High-speed connectivity, some of them are lower speed than the others, show you what the speed is in different areas that they use. Structured cabling, equipment room, location of significant networking hardware such as servers, mainframe hosts. We've seen that one, haven't we, the equipment room? Where would the equipment room here be? Over in the NOC, where we were the other night. And there were some cabling in there, not necessarily pretty cabling, but there was cabling in there.
It was all jumbled up a little bit.
Some of it was, some of it wasn't. He's trying to clean it up, but it really is when you start doing that. It is difficult to keep that stuff sorted out.
See the Pepsi cabling where it's shaped like a Pepsi
Is it?
bottle cap thing. Same colors and everything.
Telecommunications closet contains connectivity for groups of workstations plus cross connection to equipment rooms. Cross connection, and we talk about cross connection. This punch-down block is called a cross connect. And what it allows you to do is bring the wires in, punch them down, and then take them to someplace else. If you need to change it, you can change it at the punch-down block without running the whole wire over again. This one's an old one. This is a old telecommunications punch-down block called a 66 block. I don't have a 110 block. I've got a video. We'll make you watch the videos that I found here in a few minutes. 110 block, 66 block, how to punch them down, how to punch down one of these things also. And those are what we want to look at. Horizontal wiring connection, connecting workstations to the nearest telecommunications closet. Where's the nearest telecommunications closet here? Those things would be the telecommunications closets. They're not really in closets. Well, any time that you concentrate, a concentrator would be a telecommunications closet. So we go there. We go to our actually this probably be an intermediate facility. Telecommunications here. There we don't have any really telecommunications here. Work area encompasses all the patch cables and horizontal wiring necessary to connect the stuff together. Stuff, that's a good technical term, isn't it? Many network problems, and I agree with that 100,000, 10,000%. Poor wiring, making the wiring wrong, not paying attention to it, not keeping a wiring diagram. And it's not easy to do, because you got to do this and you do this and you get in a hurry and you do that and you connect stuff together and you forgot and you didn't make an update to the wiring map, to the wire map. And now you got to go troubleshoot something and the wire map's out of date and none of your troubleshooting works. If that's not right, you're going to have some real troubleshooting problems when something happens. Trust me on that one. Two methods of inserting UTP twisted-pair to RJ45s, the EIA 568A and the 568B standard. The 568B standard is the one we use, and I think it's the one that is currently approved. The 568A, according to some of the stuff that I read, is supposed to be defunct, except I understand the government requires that you use the A standard. So they made it defunct and then required you to use it. That's typical, isn't it? Straight through cable allows signals to pass straight through between terminations. I'm going to give you a really simple rule here on when to use a straight through cable and when to use a crossover cable. Like to like, same to same, computer to computer, hub to hub, switch to switch, computer to NIC on router, use a crossover cable. The reason you have to do that is we got 4 wires that we use, 2 of them are transmit, 2 of them are receive. And when you go from a like to a like, you've got to send a transmit to the receive. Can't do that, can I? Transmit to the receive, and the transmit, we'll do it this way, and the transmit to the receive from back.
Extra credit if we get it?
Hmm?
Do we get extra credit if
You get it, yeah. So you have to do those things. If you use a switch or a hub, we plug a computer into a switch or a hub, we're going to use a straight-through cable because the hub or the switch electronically does that swapping for you so that you send it on the transmit, it sends it out to the other stations on the receive pair. So like to like is a crossover. Everything else is a straight-through. That's a pretty simple rule, right? Yes?
Can I ask a very, very curious question?
Uh-huh.
Can we take a break right now?
Sure. We take a break? Let's take a break. Let's finish this up. So, what uses a crossover? Router. What's the?
Like to like.
Like to like. Like to like uses a crossover. The others use straight through. Crossover termination locations to transmit and receive wires on the other cables are reversed. When you look at the standard, what happens is 1 and 3 and 2 and 6 in the numbering system are crossed. The best way to do this is have the 2 color codes out there. One end you make an A and the other end you make a B. Then you have a crossover. If you want a straight through A to A or B to B, we normally use the B to B for the straight through.
Will a crossover work
because because you have crossed the wires that you crossed what you've done when you cross the transmit wires with the receive wires. So instead of sending it to the switch on the receive, it sends it to the switch on the transmit. The straight throughs here, and if you look at this, green and white, green, this is the A standard. The A standard starts with green and white. The B standard starts with orange and white. This is a B on end A. I don't know why they should have done it the other way around, shouldn't they? A B standard on end A and an A standard on end B. But it's important that you keep these things straightened when you go through your wireless. Everybody's favorite. Wireless really is becoming a bigger and bigger and bigger deal because everybody's running around here with wireless devices.
Have you seen the wireless SDHC cards for like cameras?
Mm-mm.
Yeah, it's got its own wireless connection that connects to your computer to instantly share the...
Is that right?
Mm-hmm.
Wow.
Once it gets within a range. Yep.
Gee whiz. So it actually connects to the card itself?
Yep. I saw that. We sell the battery power off the camera or whatever.
Wow. That's pretty amazing. No. I don't have anything sophisticated like that. My car is built in 1983.
What is that? Do y'all know what the technology is to connecting?
Just Wi-Fi. Standard wireless. Yeah.
Wireless, the devices have to use unregulated frequencies because everything else regulated, licensed by the government, you got to go get it allocated. The wireless, the unregulated wireless bands are the 5 gigahertz and the 2.4 gigahertz and the 600 or 800 or whatever it is the original phones were on. Those are unregulated. Anybody can use them. The problem with anybody using them, if somebody interferes with you, anybody can use them. There is no regulation in that. If you had regulated frequencies and somebody got on your frequency, then you can do something about it. But unregulated is unregulated. These are the two standards, the A standard and the B standard. Again, straight through. When you make your cables, use the B standard, straight through, B to B, crossover, B to A. And we have testers up here that we'll test them with. The wireless spectrum, I kind of got that in the middle of that, didn't it? Radio navigation, this is in the book, the things that are there, FM radio, television, L-band, all the things that are regulated. Wireless LANs are up here in the same area as the C-band satellite, the 2.4 gigahertz area. All of this stuff down here is regulated. The unregulated frequencies, anybody can use it. You don't have to get FCC permission to use those frequencies. Nice picture of characteristics. One of the things that you do when you connect wireless access points together is, or put them in the same vicinity, to connect with other systems. They really need to be on different frequencies. And if you look at this, take a look at this chart over here when you get a chance. This is from Fluke Networks. It's got some information about where the channels are. There are actually, in the B and the G, there are actually only 3 true channels, 1, 6, and 11. All the rest of them have overlap. And this will show you, if you look here, this will show you the overlap. These are the 3 distinct channels. The 2 and the 3 and the 4 overlap the other ones a little bit, so that when you look at you putting your wireless access point in, there are other access points around, you want to go away from where those are. 1, 3, and 6 are the only true channels. This has got the A in it and how you would set up these things to separate the channels. Here, this little thing, and if you set them up in cells, so that you can do those things. Antenna patterns are kind of a different thing. If you want to play with antenna patterns, use that Cisco game link on the web page, on the Moodle page, and go, and they've got one game in there where you you go do wireless coverage for the aliens, and they'll go through how the antenna patterns work for the Yagi, for the directional, and for the omnidirectional antennas. What kind of coverages that you can give with it. It's kind of a neat game to play to get an idea of what you can do with wireless, as well as what's going to happen to your signal when you get things in the way, like big metal boxes. Directional antennas issue signals in a single direction. Wireless has got a standard. Wireless goes, what, 300 meters? Does that sound right? Is that what the advertised distance is? 300 feet, 100 meters. Just like the 10-base T stuff, right? Or the T stuff. That is with nothing in the way. Perfect conditions. Omnidirectional antenna. Can it go further than that? Absolutely. Directional antennas. If you want to, I think, see something interesting about antennas, Google Pringles can antenna. Yes, it's real. It goes longer distance. Omnidirectional, everything goes in the same direction. Geographical antenna or the wireless systems can reach the geographical area. Atmospherics can make a difference. Where's it going to go? What's in the way? Walls obviously make a difference. What kind of walls? Steel walls are going to stop things. They make some stuff. Somebody in the government's using it. I don't know if you guys probably didn't use it, but made some window film that stops wireless signals, because one of the things we talk about all is how to get there and how to connect them together, but you really want to kind of confine your wireless signal. Most businesses don't really want their wireless signals to go away very far. TJ Maxx wished theirs hadn't gone away very far, because this is the one that managed to lose 45 million credit cards through their wireless. But these omnidirectional, what are we going to do? Lots of things. Signal propagation. That just shows the bouncing the signal around, and those do happen. RF is not the only wireless signals. There are infrared. That's what I'm using right now, right? An infrared transmitter. No. Infrared really is confined. If it won't go through walls, obviously, like the radio signals will. Different obstructions are going to cause the signals to go different ways. They will reflect. And when they reflect and refract, it can actually change the signal, so that you may have to move the access points around in order to make them work. The best place in a building is normally to put it as close to the center of the building as possible, so that the omnidirectional antennas go the same distance in each direction. You may need, in a larger building, you may need, with lots of walls or whatever else, you may need more access points. We have a problem in this building. In the office back where the nurses are now, and on the other side of the lounge, that wall back there is a physical firewall. It's a cement wall with rebar in it. It's very difficult to get a wireless signal back in that part of the building because of the material that's in the wall. It gets there, it's a very, very weak signal. Signal degradation, changing in signal strength from electromagnetic energy being scattered to things we're talking about being bounced around. As it gets scattered, it becomes less concentrated. The signal will become a little bit weaker. And we've talked about diffraction, reflection and diffraction. All of those things can cause the signal to degrade. And honestly, you only want the signal to go so far. You want to be able to control where it goes. So degradation is not all bad. But somebody with a good directional antenna can probably sit down there at Wendy's and get a signal on your wireless access point. Are they going to do that to yours and mine at home? Odds are against it. But a business Oh, let's say when Best Buy had their wireless point of sale machines in the parking lot, having this big parking lot sale, and we're sending the information back into the building on the wireless with no encryption on the signal. Would people want to listen to those things? Yeah. Some things they do, some things they don't. Some are worth attacking, some are not. You should take precautions, all the precautions, all the time about these things. Experience attenuation, just like everything else. All of these things are going to have attenuation. Attenuation, another good term, right? Attenuation means the farther you go, the weaker it gets. Interference from atmospherics, there's lots of things that can interfere with the wireless access points. The most popular ones, microwave ovens, portable telephones, wireless joysticks. I mean, you could go on and on and on with a list of things, because most of the portable wireless equipment is going to use the 2.4 gigahertz range because they can. It's the unregulated range. You don't have to lease that spectrum from the government in order to use it. Narrowband, broadband, and spread spectrum signals. That's hard for me to say. These are just ways to try to make the things better. Narrowband concentrates the signal. Broadband is a relatively wide spectrum, a lot of throughput. Spread spectrum uses multiple frequencies and frequency hopping. This is a technique that these Army guys use in order to try to maintain security of communications. Hey, what?
Frequency hopping.
Frequency hopping, yeah.
Because you have to be.
Yeah, because you have to be programmed. Both of them have to be aligned, right?
They have to be within like 3 seconds, and if they're not.
Frequency hopping, the transmitters and the receivers change frequencies on a regular basis. Spread spectrum uses a broad range of frequencies and puts a little bit of information on each of those things. These were really cool when they came out, but they're pretty easy to detect now. There's all this automated electronic warfare equipment. In a military sense, all of this stuff can usually follow those frequencies around and stay tuned. Fixed versus mobile point-to-point, efficient use, fixed wireless systems, location of the transmitter and receiver don't move. Mobile, we can move the things. I guess a fixed wireless would be maybe like a radio station. That'd be pretty much of a fixed wireless, wouldn't it? In a broadcast environment. Be located anywhere within the transmitter's range, and these are the things that you can move around, and you may need to move these around based on things that go into the building. Infrared we talked about briefly, and that's how much we're going to talk about it. Frequencies 300 gig to 300,000 gigahertz. That's a pretty high frequency, isn't it? What was the rule about the higher the frequency? How did frequency and range relate?
Higher the frequency, the shorter the range.
Higher the frequency, the shorter the range. These are not long-range devices. The new cell phones, now some of the older cell phones used to have infrared sync ports that instead of using Bluetooth, you used infrared to do that. Infrared can make your wireless secure. If we put an infrared system in here instead of a wireless access, instead of an RF wireless, we'd probably be relatively secure, wouldn't we? Ain't gonna go there.
A lot of laptops and stuff don't come with it nowadays.
Hmm?
A lot of laptops and stuff don't come with it nowadays.
I know, but you'd have to configure. You also have to configure the room because you've got to bounce those signals around correctly. Infrared, very short range, they will bounce around. Typically what they'll put is some on the ceiling to bounce the signals around so that they can get detected. And yeah, you'd have to, probably going to have to put some sort of an adapter in it in order to use it. It's not something that you see every day, except for your remote control. I'd say usually infrared, isn't it? Got to be close to each other, line of sight path. Throughput rivals fiber optic, it can. This just shows a picture of PDA and computer syncing, and again, and he's right, most computers don't come with infrared ports on them anymore. The only one, I had a laptop, an older IBM laptop that did have an infrared port on it. The ones that I see lately, I don't think do. You guys that sell them would know. But I think that they're probably mostly not there. Wireless LAN architecture, more and more popular. Printer, computer, everything connecting wirelessly. And I think there's probably going to be more and more of that because it's convenient. When you start moving something, instead of having to go and make a wire, which we're going to do, put the wire in, you just move it. That's one of the things that makes voice over IP popular. When we want to move the telephone, all we got to do is go plug it into a port that goes to the switch that has the ability to run it. More LAN arc. This one's getting pretty fancy here, isn't it? 2 access points, and on and on and on. Problem with wireless is slow. We talked about full duplex. Full duplex, 100 megabit full duplex. We get 100 megabits in each direction, which gives us 200 megabits. 100 megabits, and we'll pretend we'll have a pretend frequency throughput here. 100 megabits because I can do that well. 100 megabits would be half duplex, and you're going to get like half the speed because when a workstation wants to get on the wireless, it sends a request to send, and the workstation gives a clear to send. Because if you do these things, how are you going to detect? How is your wireless access point going to detect that some other wireless access point is trying to connect? Because if I have a wireless access point that goes 100 meters and I'm 100 meters away and Robert's 100 meters away, we're 200 meters separated. We can't talk to each other. The only thing we can talk to is the access point. It has to control traffic. That's one of the things that makes them really very slow. What's a great way to tie up an access point? Stream a movie. Because you can, hey, my turn. No, not your turn. My turn, no. And that's what you're really saying, my turn. It's in the media access, it's called a collision avoidance. You have to have permission in order to do that. It avoids collision. Ethernet's collision detection. If you have a collision, it detects it. This uses a collision avoidance. And we're finally at the end. You thought we'd never get there after 2 nights, didn't you?
It's starting to look like it.
A lot of terminology in this chapter. A lot of terminology in this chapter. I think that a big part of the learning these things is terminology. So we looked at a lot of different things. We talked about analog digital, multiplexing. We talked about throughput versus the theoretical throughput versus bandwidth, baseband, broadband, single frequency, multiple frequencies on the same piece of media, noise, what noise can do to the channel. Analog and digital attenuation, what is attenuation? Cable length contributes to latency, and the type of cable that you use. Each of the cables, and there are specifications for these things, each of them is going to have a different latency. The information is going to be able to travel faster in different ones. And that's kind of obvious with the 10 base T and the 10 base 5. And the 10 base 5, based on what we've said about how this stuff works and the timing, why can't I go 500 meters on one and 100 meters on another one? They got to be going faster, I'll tell you. If it's based on, yeah, they do. How else is it going to work? How else are you going to be how else are you going to be able to detect something that happens 500 meters away in the same amount of time that you detect something that happens 100 meters away? If we put you out on a track and said you've got to run 500 meters in X seconds, and you got to run 100 meters in the same X seconds, you're going to have to run a lot faster on the 500 meter stretch, aren't you?
Yeah.
Same thing. Same thing.
It's just a faster,
It's just faster. Different media has different characteristics, and but basically it's based on impedance, because the less impedance, the less degradation, less signal degradation, all sorts of things. Coax had the central copper core surrounded by the plastic coax, because it is coaxial, because everything is a coaxis. Twisted pair we looked at, color-coded. We had two standards, the A and the B standard. We're going to use the B standard when you make the wire. Two types of twisted pair, shielded and unshielded twisted pair. Shielded has better resistance to noise than the unshielded. Number of physical layer specifications for the Ethernet, fiber optic. We looked at fiber would be our preference, except it costs so much to make it, because it's immune to EMI, really high speed, really clean signal. I'm sorry?
Signal's not traveling outside the wire either.
Signal's not traveling outside the wire, no radiation from it, nobody can detect it. If somebody taps into your fiber optic network, you'll know about it, because your signal strength will go down dramatically, because it's light, and if somebody taps in, they've got to share that signal strength. How hard is it to tap into an Ethernet network?
Hard,
Really?
maybe.
How hard is it?
Not that
What do you got to do?
No, it's like there's devices that you can just set beside the wire.
It depends on what that's there, but why do that? Why don't you just plug into the port? That's how hard it is to tap into an Ethernet network.
That's really
You just
easy.
plug it in. It's really easy, it is. You have to have something there to plug it in, and the thing that Chris says, there are devices that will detect those signals.
So, I mean, you're not even on the
Yeah.
network. You're just
Not anymore, I know, you're just using you're using the electromagnetic change in order to induce the current. Single mode, multi-mode fiber, structured cabling, the cabling inside the building itself. Best practice for cabling and follow these standards. I had a class one time, and everybody's saying, oh, the Army uses this standard. Well, at work we use this standard. Well, someplace else we use this standard. Okay, just make some cables. Let's see. And most of them would work. Actually, all of them would work as long as you went, 1 to 1, 2 to 2, 3 to 3, 4 to 4. It didn't matter what the color code was for short distances. But if you try to go long distances, the one that didn't meet the standards, we had 100, this was 100 megabit, we had a 100 megabit port. Well, those that didn't meet the standard could usually go all around 10 megabits. So the standards really are important because of the way that the wires lay inside the cable. And that's for mostly for noise reduction. It's the same thing, and I'm sure that's one of the issues with this one back here I talked about. It's in the 100 meg port that actually goes to a gigabit port at the other end. It has to either the ends are bad, and we had one in this room that was that way. They finally put a new wire on it, and golly, it worked, because the connectors weren't made quite right. So those things, testing those things, the tester that I have here just going to check to be sure that you have connectivity. There are testers, more expensive testers, that you can load test the cable with. If you're doing things that are going to have a lot of data, you may want to do that. They made a bunch sometime. The first time we put in twisted pair, and they did it wrong for a number of reasons. They did it wrong. You could log on to the server, but when you started to try to transfer something, it just said thank you, but no, because the standard was wrong. It was interfering with itself. Infrared short distances, probably easier in a wireless environment, easier to keep private, obviously, than the RF, because the RF is going to go everywhere. So our questions? Why are you grinning? I just haven't everybody got questions.
So you look